Okay, thank you very much. Thank you for inviting me to this workshop. Today, I'd like to talk about. Well, we didn't hear anything from Christian. He had some projects. He wanted to present some projects from West Africa and Southeast Europe. So I will continue now with the Austrian part. And next slide. Okay. First of all, I'd like to start with these slides. You see here some impressive erosion processes. We see that the human intervention in rivers impact on the sediment balance, and this situation also influences somehow in some places flooding events. So you see here, obviously we have a shortage of sediments in rivers and on beaches with these impressive erosion processes. And why does this happen? The main reason is that we are damming our rivers, and we are damming almost 50% of our rivers worldwide. Don't want to go into detail, but you see here on these two pictures the positions of coarse and fine material in a reservoir, and all in all, as we know, about 1% of our reservoirs are lost in our per year on the whole planet. Well, when we talk about changes in floodings due to climate change, we can look as a good example on the IPCC report. From this year, so we know that climate change's effect, and we all know about these catastrophic effects which might happen. Although the probability is quite low, it was quite low, but nowadays we really talk about the collapse of ice sheets and so on that might have really huge impact on our planet. And a lot of people will be impacted, influenced by this climate heating process. Also in the report, it's written about 1.5% increase will lead to irreversible consequences. I think, well, we will see what will happen, but I have two screenshots here from an Austrian newspaper. What we can observe nowadays already is we see on the left side, we have problems now starting our ski season because we don't have any snow anymore on the mountains now this year, or also on the right side in October this year. This was the warmest, at least in Austria, the warmest October forever. And it's really a signal for catastrophic development, which we have to look at. Well, while I'm talking about this, I'd like to talk about a project, quite a small catchment area in Austria, where we already can observe, or maybe we observe already this impact of this climate change. So the project, these were two projects between 2012 and 2021. We started last year. You see here in the middle a map of Austria and the small catchment area, the Schöttelbach, which is then flowing into the Wölzerbach and then to the Mur River, which is one of our major rivers in Austria. So it's really small, 70 square kilometers. It has quite an interesting geology because it's a mica slate, mica schist and gneissic area. That means it's a very, very soft and erodible sediment or rock. And what what is typically in this area is that we have here very deep, easily erodible glacial, ancient glacial reservoir sediments. That means on this, the first tests when we started the project, we did some geoelectric and geoseismic investigations. Our colleagues from the University of Graz did it, and they found out with these methodologies that about 100 meters of glacial sediments are there, and the river is flowing within these sediments. That means there is more or less an infinite number of sediment available which can be eroded in this river. And the catchment itself, we know that it's quickly reacting. It's quite steep. That means if there is a rainfall, then it reacts very fast. At the end of the catchment, on the right side, you see again this observed catchment. There is the city of Oberwölz in the lowest part, and a few hundred meters upstream, there is a sediment retention basin to protect this city. And in the project we started with that, we installed quite many measurement systems starting from meteorological to sediment transport measurements and so on. I will give you some examples soon. So what happened? So as I said, we started in 2012, but in 2011 there was a big flood event. You see this on the left picture. This is this catchment, and these are some radar data of this event. You can see here a maximum of precipitation within 50 minutes of 90 millimeters. So all in all, we observed there in this location about 140 millimeters of rainfall within 3 hours. And this was really a very local. These are very local events. At the outlet of the catchment, there is almost no rainfall observed. We had a maximum discharge here. The maximum discharge was about 100 cubic meters per second during this flood. So a very, very local pluvial rainfall event. Yeah. And in 2017, this happened the second time. You see this on the right side, little bit less, but still it had a similar behavior like that one in 2011. So what happened during these two events? These are some pictures from the second event, but it looked the same at the first event. We observed really lateral erosion, massive driftwood, which entered the river. A lot of wood was transported along the river, and you can see here some images how that worked. And a lot of bank erosion happened during that event. What you can see here. Some impressions from the first flood on the left side. So we could observe sediment transport of boulders, which are the size of the small cars. They were transported along the river. Then I mentioned already this wood which was transported during the flood event, and the problem if you have such a river like you see here in the center, if you have bridges and you have that amount of wood transported, then you observe this blocking of these rivers and then this overtopping of the river banks, these channel banks, and then the flooding which happened then in the surrounding area in the city. Some impressions from the event 2017, how that looked again. You see in the left picture these erosion processes that happen in this river because of this very mobile, very fine material which is there existing. Sorry, some impressions. The damages were several million euros. Luckily, nobody was injured during this event, but it was still quite huge. And as I mentioned already, there is a sediment retention basin upstream of the village. which you can see here on this aerial picture. The volume of this sediment retention basin is about 35,000 cubic meters. And the first event, it was a little bit problematic because already half of this reservoir volume was filled up with sediment. So only about 15,000 cubic meters were left, and this was filled within a very short time, filled up, and then all of the sediments then over top were transported downstream in direction to the village. So the retention basin obviously is too small, and it was too small here. Also not only in the rivers, we could observe some damages here. You can see in the left picture some landslides, so some transport processes also not on the river side. And on the right side, interesting was that you see again here this very local event. There is the main river, which is where we observe the flood, and then you can see flowing from bottom to top this small tributary to the main river where almost no water was flowing. That means it was really a very, very local. These were very local events, and that can be seen here in this picture quite impressively. Well, and then this overtopping, the sediments which were not trapped in this basin, then of course they were transported downstream again, and then you can see here problems which happen in that case, that deposition of sediments occurred within bridge cross-section. Bridge cross-sections, that means that is also a big problem if that happens, because you don't have this cross-section anymore available for the water. Then you have this overtopping and this flooding event which happened here. Yes, and then the sediments, of course, during the events, it was tried to dredge out the material, and also after the event, of course. And this material then was brought by trucks to some agricultural areas, and that is deposited there. This is also nowadays it's getting more and more problematic, because we observe these events. We build a lot of sediment retention basins. We trap the sediments, and then we have to deal with the sediments at the end. So we have to dredge it out, and we have to deposit somewhere. Well, this is also quite a challenge. So in this, there are some open questions, which we tried to look at when we did the project. First of all, was the catchment area is already disturbed by events. What does that mean? Because when you have an event, which was, for example, in 2011, then you have these open riverbanks, and then if there is next event, then of course the might result in more sediment, which is then transported because it's on open areas. So what amounts of sediments are available for transport? Another question, does this climate warming lead to more sediment transport, increased sediment transport, also then of course in the danger of flooding? And open question was also the small or the recommended volume for a new retention basin. So to look at these questions, we did a lot of measurements here, only some examples, and also we did some modeling. And now today I'd like to give you a few impressions of these things. Measuring meteorological rainfall was done in the catchment in several locations with such instruments. So rainfall and also the snow accumulation during winter with some radar systems. And at the end, at the lowest point of the catchment, you see this on the right picture. Here, there was our main gauging station, which is in the center, shown in the center, quite a good station location for that. We have this rectangular cross section. On the riverbed is then mobile. So there we did some measurement with radar systems, water level, velocity. That picture you see already. See some calibration measurements with an active probe, and classical way to measure here turbidity, temperature, and so on. But the problem, which you can see on the right top picture on the top, this picture was taken short after the second event. Yeah, you see already here quite massive sediment bank, which is still in the cross section of our measurement, and this leads also to a big question, which we think is really important. That usually, if you look at rating curves from hydrological offices, they don't take these things much into consideration. That during an event, you might have huge sediment transport, which really changes your cross section. So then the rating curves are not valid anymore. And within this cross section, we could see this quite well. That rating curves, which you first measure with some probes, which you define with some probes, which you extrapolate because you don't have the measurements during high floods, they are not very accurate at the end when you have a flood event. Sediment sources, this was done by colleagues from the University of Graz. They did a lot with this mapping, laser scans with airplanes and also with drones, terrestrial laser scanning. Here on the right side, you see some findings. They did it with a drone scanning instrument. So with that, if you do this for several times, then you can observe where are the locations where you have this erosion processes and where do you have this deposition processes. We did tracer measurements. That means we used on one hand colored tracer, that we took gravel out of the river and colored it. Of course, you weight it and you measure this, bring it back, the color tracer, and then you observe the transport of the single stones. Or you use this, radio tracer system where we dredged holes into stones and we put in these radar transmitters, and then you can observe the transport of a single stone, which you see on the left side, some example how that looks. So you have to transport the distance in correlation with the discharge, or you can try to find out what is the initial motion, so which grain size starts to be transported in the river reach at which discharge. So of course we need, for larger stones, you need a higher discharge to start the single stone to be transported, and these are also findings which you can get when you use such tracer methods. One important thing in our project and also in other projects are our sediment impact sensors. We started about 10 years now with developing such sensors. At the beginning, they were quite simple, very simple, only metal plate, and on the bottom of below the metal plate there is an acceleration meter. You install it somewhere in the river on a boulder, or as you can see here in this construction, which was built for these measurements, where we installed these sensors, and it works like this acceleration sensor we have in our mobile phones, for example. If you hit on it, then you can measure the acceleration, and the stronger the hit is, the more acceleration can be measured. Of course, as I said, we started 10 years ago. Now we're still developing these instruments. It's really a tricky thing. We did some calibration measurements in the laboratory, where we installed such a plate, and we added some sediments, and we tried to find out. We tried to define such calibration curves, which you can see here. So they are the impacts, number of impacts in correlation with the mass. So in that case, it's a linear function, but it's a problem when, or it's not so easy to do this in the laboratory, because the laboratory always have some constraints. So then we try to do some field validation measurements with such traps. Here is installed cyst here on a natural rock, but it's really tough, because usually when you can do such measurements, you don't have any sediment transports. During flood events, you cannot do any measurements anymore, because you cannot enter. So it's not so easy to do such things. And at the end, this is an example from the first project, from our first impact sensors. You see here these blue bars showing some rainfall events, and the red bars, the sediment impacts counts in that case. So it's only the raw signal which is shown here in this example. Well, this was mainly done by our colleagues from the University of Graz. They did all these mappings and then scannings along the rivers, and at the end they developed such a sediment balance. So at the end they estimated, or they measured how much sediment is entered into the river on which location, and this is the retention basin. It's 30,000 cubic meters during the time of between 2012 and 2017. About 35,000 cubic meters were dredged out of the material, and at the end 80,000 cubic meters were flowing over the basin dam. So these were some examples of measurement methods which we developed there, which we used there. As I said, we did some modeling too. This hydrological modeling was also done by our colleagues from the University of Graz. Stephanie Kesendiner did it, and we wanted to use this hydrological model mainly for getting an idea when we don't have any measurement data. So mainly in the future events, of course, are interesting. So she used this Wasing model for this purpose, and on the right side you see already the final calibrated model of these two events, event 2011 and 2017. These were these discharges, and these are the model, the final model results. And when we look then at the future in our catchment, which is interesting, we can use, for example, this. It's called OKS15 flagship styria. This is a map of our styria, which shows that we have a mean value, a mean temperature for over the whole year of about 6.6 degrees Celsius, and this climate scenario, RCP 8.5, which is quite a strong, tough one, shows that we can estimate about an increase of the mean temperature over the whole province of about 4 degrees Celsius. So in all models, also the not that strong ones, show that quite a clear temperature signal, an increase of about up to 4 degrees. If we look at the precipitation, our models show that we can expect that in winter we have an increase of rainfall or precipitation of about 24%, and in summer we can expect less rainfall here. There are different, because it depends on which part of the province you look at. Yeah, and with this information, Stephanie tried to do some modeling of future events. What can we expect? And you can see already. I'm sorry I didn't hear the first presentation of Richard, but you can see here there are really huge uncertainties in future events, depending what you as an input in your model. And at the end, she defined this flow hydrograph as a conservative hydrograph for the future, which we can use then for the sediment transport modeling as an input. This was done by my colleague Sebastian Gegenleitner, and he used for the sediment transport modeling the model Telemac and CSIF. It is really a challenge to use a 2- or 3-dimensional model in such torrents. You can see here, usually sediment transport or models are used in lowland rivers, where we have fluvial transport processes. In torrent rivers, it is really different. We have some debris flow. Sediment availability in bed is very low, but we have a lateral sediment availability, and therefore really huge uncertainty how much sediment is entering the river itself. So Sebastian then developed the model a little bit. So he implemented some sediment transport equation in the code from Rickemann, which can be used in these torrential rivers. At the Störtelbach, we did our modeling. For calibration purposes, the hydrodynamic model was used in the middle course, and then for the outlet, some modeling of the hydromorphology was done. So this is, again, you see this old barrier, which is located here. There is the new barrier already, I'd like to show you later, located about 650 meters downstream of the old barrier, and here is the village of Oberwölz. Some results from the modeling input was the calibrated hydrograph from the rainfall runoff model. The two events you can see again, and here are some depositions in the old retention basin. 2011, if you model this without any lateral inputs, then we could observe about 10,000 cubic meters of deposition. And if you implemented the model as lateral sediment input again too, then we could observe a deposition of about 24,000 cubic meters. This was in 2011, and 2007 similar, between 15,000 and 32,000 cubic meters of sediment. See already the numbers are higher between 2011 and 2017. Of course, these findings were then compared with some measurements which were done. So these volumetric measurements of the basin. In 2011, we measured about 15,000 cubic meters. This is in between this minimum and maximum value I showed you. In 2017, the basin was quite empty, and here we could, when we compare these measurements with these numerical simulations, you also see that we're quite good. Fits quite well, yeah. So this was the sediment transport modeling of 2011, 2017 without this new barrier, and then in the future, which also worked quite well, but it was really difficult, or it is difficult to get a number of how much sediment is really then transported over the old barrier to the new barrier. There were really too many uncertainties, and we at the end could not give a number in the project, because it was too uncertain. Yes, I would say. Well, to summarize, the measurement, it showed that really we have it's really a challenge to measure sediment transport in such rivers. The impact sensors will be improved. We're still working on this system. The modeling, it showed that we have a change from nival to pluvial regime because of this increase of the temperature during winter time, which changes the regime in the system, and the uncertainties are really high in that case, depending also on the chosen climate scenario. So if you take a different scenario, you get really different results. Sediment transport models also, uncertainties are really high. It is not so easy to divide between bed load and suspension load. Then also the uncertainties concerning this lateral input. So along this river, it's really difficult to estimate the sediments which are then entering the model, and the wood is also problematic. So we know that about most of the sediments in the 2011 and 2017 were not trapped in this sediment, in this retention basin. In general, I can say that the increase of an increase of rainfall events, of heavy rainfall events, and also an increase of intensity of sediment transport and flooding can be expected out of this project due to this climate warming. We could measure, and also we could calculate more sediment transport in 2017 than in 2011, although the precipitation intensity and so on, and also the runoff was slightly lower. And this showed quite impressive that this open river banks are more endangered to be eroded again. So if you remove the vegetation, of course, then you have higher sediment availability. Yes, it's shown here. Okay. At the end, it was quite clear that a larger debris barrier, a larger sediment barrier is necessary to prevent this downstream flooding. So this sediment, which is not trapped in such a barrier, influences really the flooding in the downstream reach. So we can say at the end, climate warming will lead to more local heavy rainfall events, and this also might lead to higher floods, or will lead to higher floods, but also the changes of the sediment transport will have an influence on the floods, as I mentioned already. So at the end, between 2017 and 2019, a new retention dam was built, 15-meter high, quite large construction. The volume is about 140 cubic meters, and this new retention basin, in combination with the old one, which is still in operation, should then really protect the downstream village. Okay, so thank you for your attention.
Thanks, Josef, for a very nice presentation. We are running a bit out of time, so I think we have time for one question, if any. I don't see anybody here. Maybe anybody connected from remote. I don't see the chat box, so I don't know if anybody is posting questions. No, Paula is saying me not. So in that case, so Josef, thanks again for the presentation.
Thank you very much.
Thanks.
As you know, our webinar also features a poster session delivered by our young researchers. And within the context of these events, the department has promoted an award recognizing an outstanding poster contributions with the aim of acknowledging the commitment of our young researchers to excel in a national and international scenario through favoring a broad visibility of their research activity. Many of our young researchers took part to the selection with excellent quality posters and ensuing video presentations too. You can find their posters as well as their videos on our department website. I invite you to give them a look as they are really good. Maybe if we have time, we can share some of them after during the coffee break if we'll have time. Anyhow, among them, two outstanding contributions has been awarded the Young Researcher Prize, which means that a total amount of 500 euros has been granted for open access publishing of their research papers. As I said, everybody did a great job, but we could only pick two as winners. And the winners of this fourth edition of the Young Researcher Prize are Monica Corti and Veronica Herrera. Veronica's poster is titled Modeling Vegetation Roughness and its Impact on Flood Propagation, the case of River Piave in Italy. Congratulations, Veronica. And Monica's poster is titled Post-Wildfire Monitoring for Hazard Mitigation in Alpine Areas. Congratulations. So congratulations to both of you for your great job. I invite you to give a look to their poster during the coffee break, not now, but during the coffee break, you can enjoy looking at the poster while having a coffee. We start again with this second part of our seminar, and we will have 7 presentations from different professors of our department. So let's start with the first one, which is Claudio di Prisco, and we will have a presentation on landslide risk mitigation. So please, you have.
Okay, first of all, thanks to the organizers and thanks to all of you. You see the subject is a bit different with respect to the previous ones, and we will talk about landslides. And the keywords of my presentation will be landslide, of course, modeling, because the idea is how can we use modeling to reduce the uncertainties, and how we can use... It's better. You hear me better? Okay. So the second keyword will be modeling, because I'm convinced that we are engineers. So we can use models to understand the physics and the mechanics in our case, and we can reduce the uncertainties. So we can design structures in order to mitigate the risk, and we can reduce the costs for risk mitigation. So this is the aim of our work here. So, no. So, a brief outline of my presentation. First of all, I have to introduce a subject, so it means I will try to define the boundaries of the type of landslide that we will consider. And in particular, we will try to describe sheltering structures, so protection structures. So we will not take into consideration the inception phase of landslide, but we talk about the propagation phase and the arrest phase, or the impact, the flowing masses against the sheltering structures. And after that, we will try to describe very briefly what we do usually when we design this type of structures, and what we have done here in Politecnico to improve the knowledge or to introduce new models in order to better design this type of structures. And finally, we will try to describe very briefly what we are likely now we are doing to solve this problem. So first glance to all our friends collaborating this subject in the last 20 years, and in particular a picture of Professor Nova, who taught here in Politecnico and introduced the use of models in one of the person introducing the use of models to better understand the mechanical behavior of soils and solving also boundary value problems. So first of all, I said we have to define the subject. So when we use the term landslide, we have in mind a very large class of phenomena. And in particular, we have two different types of landslide. We have the landslide that are characterized by diffuse mode of failure. In this case, we have a large mass flowing along the slope. And in the other case, we have a localized failure. And in this case, we usually talk about a creeping landslide, so the movement is slow. Or in other cases, if this landslide takes place in a rock, or in a rock mass, we have problems of detachment of boulders from the face of the slope. Or in other cases, we have rock avalanches, for instance, where we have a transformation of the material. So the landslide is a very nice experiment, because in some cases we start with a certain material and we arrive at the end with another type of materials. So we have a transformation as a different materials taking place during the phenomenon. Moreover, when we have flow slides, so the fast landslides are the most destructive. And in this case, we have a phase transition of the material, because at the beginning, at the inception of the landslide, the material behaves like a solid. And during the propagation, the material behaves like a fluid. So we have a typical phase transition, and even this phenomenon is very interesting, but not very well understood, and it's very difficult to reproduce it theoretically and numerically. So, in my presentation here in Politecnico Milan, we have tried to introduce new models for two different types of landslides. On one side, the flow slides, the first type of diffuse mode of failure. And on the other case, we talk about rock fail, so totally different phenomena. But in both cases, we have a typical phenomenon where we can individuate the first phase of the inception, the second phase of the propagation, and the rest for impact. The different types are characterized by different phenomena, but at the same time, we can say that in both cases, we have a lot of knowledge that we don't have. So up to now, there are many uncertainties in the description of the propagation phase and also in the description of the impact of the boulder or of the flow slide against sheltering structures. So, as you know, when we have to evaluate the risk, we can very briefly and in a very old manner describe the risk as the product of the hazard and the vulnerability. So in my presentation and the work we do here, we are more focused on the hazard. Even in case of protection structures, even in the case of sheltering structures. Why? Because a sheltering structure can modify the propagation phase and can modify the geometry of the evolution phenomenon. In some cases, describing correctly also the forces acting at the impact of the flowing mass against a structure is fundamental also to deal with vulnerability, obviously. It's a more structural problem that in the geotechnical field we prefer to disregard. So what are the types of sheltering structure that we have and that we use? You see, we can have sheltering galleries, we can have embankments, we can have wire meshes characterized by different mechanical responses, or typical hydraulic works that are used even in case of landslide. What's the problem? These structures are very characterized by very large costs. So if we want to reduce the cost, we have to describe correctly the propagation phase and the impact of the landslide against the sheltering structure. And what we do here in Italy or in Europe in order to design this type of structure. On one side, when we talk about flow slides, the first problem now is describing the propagation phase, and we use computational approaches. So we have numerical codes capable of describing the trajectory and the propagation phase. But what is, because nowadays we can use a numerical code capable of dealing with large displacements, with dynamic responses, but a very important problem is related to the use of the constitutive relationship describing the mechanical behavior of the soil. Because we have coupling, the hydromechanical coupling, because we have very large strain rates. And so even nowadays, it's very difficult to find a good constitutive relationship capable of describing the mechanical behavior under these conditions. And as far as the impact is concerned, evaluation of forces, usually we design this type of structures by using very simple empirical formulas. And the empirical formulas characterized by coefficients with a very large scatter, with a lot of uncertainties. Why? Because the problem, the phenomenon, is not well understood. The other side, when we talk about rockfall, we have approximately the same problem. And in this case, the uncertainty is mainly related to the use of the restitution coefficient, the impact of the boulder along the slope. Because if you change that coefficient, you change totally the trajectory. And finally, exactly the same, when you want to design the structure, the sheltering structure, you have empirical coefficients, empirical formulas that are considered to be correct for a certain geometry, but cannot be extended to any geometry and to any boundary value problem solution. So the one problem, I said, is describing the interaction, because in the propagation phase, but even in the impact of the landslide against the sheltering structure, a key point is describing under dynamic condition the interaction of the landslide with the sheltering structures. And so we use, again, a model, because usually we assume one side that the mass impacting is deformable and the sheltering structure is rigid. In the other case, the opposite. We can define a rigid block against a sheltering structure which is assumed to be deformable. And finally, it's more complex if you use a model in which you are taking into consideration the deformability of both the obstacle and the flowing mass. So, only some words about what we have done. So on one side, here in Milan, we try to introduce new constitutive relationships capable of describing the mechanical behavior of the material under solid and fluid-like conditions. And this implies describing the phase transition taking place at the inception in the flow slide, during the propagation, and the opposite, when from a fluid-like material, the material starts behaving like a solid when deposition takes place, or the impact of the flowing mass against an obstacle takes place. And again, we try to also describe the impact, so evaluating the forces, by using numerical codes. For instance, discrete element numerical codes, capable of describing the phenomenon locally. And as far as the border, as the rock falls are concerned, we try to introduce models capable of describing at the local level the impact of the boulder against deformable solids. And this is done in order to better understand and to better define the restitution coefficients. So in this case, I have a model capable of giving us the restitution coefficient, so I can reduce the uncertainty in the definition of the propagation phase. As far as the constitutive relationship is concerned, we're starting from the geotechnical side, so from the solid-like behavior. So you know that in soil mechanics, the soil skeleton dominates the mechanical response of the material, in which we have permanent force chains between grains. So we also change the scale of analyzing the problem. We're starting at the macro scale, and now we are analyzing the micro scale. And we know also that the hydromechanical coupling is considered, is taken into account by using the effective stress principle and the definition of the effective stress state. And from this side, we have good constitutive relationships capable of describing the evolving condition, but only under the solid-like conditions. So the problem was also, in very briefly, related to the origin of the axis, because when the effective stress reduces to zero, the material starts behaving like a fluid. And in soil mechanics, this point is a singular point. So the necessity of introducing a more advanced constitutive relationship concerns the possibility of changing the phase from solid to fluid, and so avoiding this singular point. And what's the role of the microstructure in describing such a phase of change in phase? The microstructure can be described under quasi-static conditions, so we have a solid-like material, but even under dynamic conditions. And in that case, the grains collide among each other. So in order to describe this phase transition, I have to introduce a new state variable, and this state variable is the granular temperature. And there is a theory, very well established, even studied here by Diego Berzi and Dalila Vescovi, kinetic theory of granular gases that are used to describe the collision among grains. So the problem was to introduce an advanced constitutive relationship capable of putting together the two ingredients. So two different ways of behaving on the material. On one side, the permanent force chains, and the other one, the collisional state where the material is agitated. And this result was obtained by starting from static conditions. So in that case, all the energy given to the material is dissipated, and may be dissipated by collisions on one side, but also by the friction when the permanent force chain is destroyed. And so by using an approach which is based on the energy, it's possible to define the constitution under simple shear condition, extend it to 3D, and so on, in order to define such a new approach, which was implemented in a numerical code, continuum mechanics numerical code based on MPM approach. And this capable of describing this evolution. The following step is related to the presence of water, right? Because normally in the hydraulic community, the material behaving like a fluid is just considered, and it is not considered like a mixture, is considered by a one-phase material. From a geotechnical side, we use considering the saturated material as a biphasic material. So we have to describe the interaction between the two phases, the water on one side and the grains from the other side. So this is very stimulating from a theoretical point of view, because introducing the constitutive relationship implies that you have to imagine and describe numerically at the microscale the interaction between grains, among grains, and water. And we know that when there are collisions among grains, you have a local increase in pore water pressure, we have a dissipation of energy during collisions. And so you have to describe more correctly the physics and the micromechanics. And this is what we have done in order to extend the constitutive relationship from dry conditions to saturated conditions. And finally, what we are doing right now we are trying to validate the constitutive relationship in this case, because we have the numerical code, we have implemented the constitutive relationship, so we are capable of solving boundary value problems. And
Thank you. Perfect. Do we have some questions? We have time maybe for one. No? If not, thank you again. We can move to We can move on to the second presentation by Andrea Galli on the protection of structure and infrastructure from natural risks.
Introduction, and thank you for the organizer for having me. Talk today is again, of course, natural risk, and I will present a point of view from a geotechnical engineer dealing with soil structure interaction problem. So first of all, maybe need some. Ok, colpa mia, ok. Questo è qua e questo è il point. Questo è il point. Ok, grazie. Well, first of all, what is risk? Well, actually, there are many definitions of risk, so I will not go into the detail. Just notice that probably insurance companies always give the most precise definition of risks. And as I told you, I will focus on risk related to soil structure interaction problem with regard to the protection of structure and infrastructure. And basically, I will speak again, landslide, on a different perspective with respect to what Professor Di Prisco has presented to us, because we will consider slow landslides interacting with structure. And when we speak about soil structure interaction problem, we are dealing with a multi-scale, because we are basically interested at the macro scale of the structure, and we usually describe this problem starting from the local scale of the representative elementary volume, and then by means of finite element method, for example, we can micro scale should be described as the local level of the contact between each grain. So there is also a micro scale to be taken into account. And our problem, our macro problem, is actually inserted within a mega scale of the entire system, and it is the scale where natural risk act, natural and anthropic risk act. For example, weather events or seismic events. So dealing such complexity with a unique numerical approach is of It's a big problem. But there is another point that it is important to be taken into account, according to me. When we speak about landslides, we are used to describe, let's say, the ultimate limit condition for an unstable soil mass and to derive an accurate value of the factor of safety, so the distance from this failure condition. So basically, we refer to the ultimate limit state of the slope. When we have an interaction with the structure, again, our interest is on the maximum force that the soil mass can exchange with the structure. So again, an ultimate limit state for the soil structure interaction problem. And since we wanted to check the safety of this structure, we usually refer to its ultimate limit state. But we must observe that these multiple systems have a different evolutionary law. So enforcing the fact that all the systems are at their ultimate limit state may be inaccurate and very often unsafe, because this system may be characterized by softening behavior. So it is really difficult to put together this ultimate limit state. One possible solution is to adopt upscaling models capable of dealing this complexity by a reduced number of variables. And in this case, I would like to cite the macroelement model proposed for shallow foundation, Professor Roberto Nova. And the idea is to describe this system by only 3 degrees of freedom, 3 actions that can be exchanged between the structure and the soil. One important property is that these macroelement models are real constitutive law capable of describing both operational and failure conditions, so completely following those parts to cope with the complex loading condition, because in our soil structure interaction problem, the loading paths are not decided by the designer, but they are governed by the system. And we also are able to take into account complex coupling effect among the load component. With respect to the macroelement for shallow foundation, we are able to define a unique failure condition, allowing to take into account all the possible failure mechanisms for this system, because as I told you, we may have a complex combination of loading. So the fact that we have a unique, well-defined failure condition allows to manage this complexity. Since the original macroelement model for shallow foundation, a lot of work has been done, even here in Politecnico, basically by introducing more general geometries, so not only shallow foundation, but deep foundation, buried pipelines. There are some attempts to extend macroelement models also to the stability of trees, and some extension towards more complex constitutive rules. So there is a lot of work that has been done. I do not go into such details, but it's focused only on small case studies, a few number of case studies that I have in this year, together with many colleagues of this department and colleagues of the Department of the Architecture, Built Environment and Construction Engineering. And the first case study that I would like to present is the case study referring to the Azione Visconti Bridge in Lecco, who is the most ancient masonry arch bridge in Lecco. It is a part of the historical heritage of the town because it is a part of the landscape of the portrait of Mona Lisa, so it is a particular important structure. From a geotechnical point of view, they have studied the behavior of the foundation of these piers of this bridge, because in 1949, 1950, some important strengthening works have been done, and in particular, the original pier was reinforced by the introduction of an encasing ring, concrete ring, and an encasing sheet pile of about 5 meters depth. This is a picture of the encasing sheet pile, and this is a view of the final encasing ring. These are some pictures taken during the geometrical mechanical survey of the bridge, going to the detail. I have calibrated the macroelement model for this foundation, and we have used this macroelement to perform some seismic analysis of the bridge together with other colleagues. And in particular, I would like to present to you the checks, the safety of the foundation, in particular comparing the behavior of the original foundation before the strengthening intervention, the present foundation the fact that we have introduced this encasing ring has, of course, increased the vertical burden capacity. In fact, the vertical factor of safety of the foundation has been increased markedly from 2 to 10. But with respect to the maximum obliquity of the loading path, nothing has really changed. So this intervention has, of course, improved the behavior of the structure with respect to vertical burden capacity, but not that much with respect to the horizontal. Another case study refers to the stabilizing intervention of a small railway 30 kilometers from Milano. This railway was built on a steep slope of about 15 meter 8, with an inclination of about 40 to 42 degrees. And the railway was subjected to slow superficial soil movement. Actually, the monitoring that we get from inclinometer shows us that the whole slope, about 12 meters, was subjected to marked displacement. But the original idea was to build a continuous sheet pile, 15 meters tall, with an anchorage in order to stabilize the system. We have tried to improve a bit this design by developing an ad hoc viscoplastic model for describing the behavior of the slope. And we have optimized the design of the stabilizing intervention by working on the velocity profile of the soil. The idea was to introduce discrete piles instead of continuous sheet pile, only 6 meters long, so about the half of the slope. In this case, we model the interaction between the pile and the soil by means of a series of macro elements, which were simply non-linear springs. So, again, the same idea. The very good idea was to balance the active behavior of the structure, so the fact that we can impose a pretensioning action, with a passive one, because an excessive pretensioning action would have induced an excessive heave of the railways, which is not acceptable for the manager of the system. So we balance the partial pretensioning action with the passive long-term behavior, and we were able to markedly reduce the measured displacement rate into the slope, not only immediately after the installation of the structure, but even on the long-term behavior, because we use this viscoplastic model to get a long-term forecast of about 50 years after the intervention. We generalized the macro model to the possible application to buried pipelines. This is a part of my PhD thesis, so it is quite an old study, but I am very fond of it. Because again, in this case, the interaction with landslides for this structure is usually developed in terms of ultimate limit state. So we estimate the maximum load that the soil can transfer to the slope, to the pipeline, and we manage all the structural behavior. In our approach, we have introduced again a series of macro elements, local macro elements, to describe the behavior, the interaction between the landslides and the soil. And we have validated this approach by means of some real case studies in collaboration with SNAM Rete Gas. This is an example of a long pipeline, 1,600 meters, relatively large diameter of 75 centimeters, and we get a good validation of the result. The black line is the numerical result in terms of axial force into the pipeline, and the black diamonds are the measurement taken from extensometer readings. This model can be used as a forecasting tool, because once we have calibrated the slope profile and we have validated the model, we can even try to forecast the future, so extend this displacement profile in order to see which are the possible failure conditions and to run fast and accurate sensitivity analysis on the mechanical parameters that affect this behavior. We have very recently applied this model, again in collaboration with SNAM, in order to optimize the positioning of the monitoring system. For example, the position of the extensometer section along the pipeline in order to get the most accurate description of the internal state of stress. These are some examples, again, on real scale pipeline. I will skip this slide. Just to present you the fact that we can really manage a real large-scale 3D program in a very way. The last point I would like to present you is the application again, of interaction concept to the design of a protection system for transportation lines, railways or highways, for example, represented by wire mesh anchored with steel plates and steel nails. The idea is to stabilize possible shallow failure mechanism. So the activation of one of the shallow failure mechanisms will locally mobilize the contact pressure between the wire mesh and the net that will in turn stabilize the system. Again, we have a complex interaction between the steel plate, the wire mesh, the anchor, and of course, the underlying soil. By studying this problem, we have developed a mixed approach. Unfortunately, this part is exactly under the... Anyway, we have a double behavior because the plate, the rigid plate, behaves like a shallow foundation, and we can again describe it by means of a similar macro element approach. The wire mesh is a membrane, so needs a displacement approach to develop its tensile strength. By mixing these two elements, we observe that ultimate limit state approach is not the most correct one, because, for example, the formability issues, the parameter J in this case is the tensile stiffness of the mesh. By increasing the stiffness of the mesh, we can observe an increased stiffness in the behavior, but marked reduction in the maximum force that can be exchanged between the soil and the mesh. And this is a result of that by using a simple ultimate limited approach would have not been. So just to conclude, why these examples are something to do with sustainability? Well, because sustainability in geotechnics, this is some definition that I've taken from literature, need a performance-based approach. Exactly what we have done, because we are displacement-based approach, so something related to the performance. Needs site-specific requirements and need to take into account soil structure interaction. So according to me, this is an important justification. Sustainability is risky. I don't know if you agree with me, because we have very often ill-formulated problems. We have a lack of information. We have multiple stakeholders with conflicting interests. So, in my opinion, scalar quantitative metrics may not always be the most accurate way to deal with this problem, as well as either qualitative multiple object indicator system may not be so accurate. So my definition of sustainability, it is a personal definition, it's nothing. We can assume that the state of our system depends on a set of natural variables and a set of anthropic variables that are the ones we are the most interested in, because our design choices act on these anthropic variables. And so sustainability means that the state of our system does not change, or at least does not change that much. So by developing this equation, we can have formally an idea that our design choice must fall within a sustainable fund of possible intervention. This is my idea. But if we look into this expression, the most important point that we like to stress is that each one of these terms, I mean, the effect of natural variable on the system, has something to do with natural science, for example. The effect of anthropic variable on the system is something to do with technological skills. The variation of anthropic action are our design choice. The variation of environmental action has something to do with monitoring activities. So again, sustainability for me is the need for a multidisciplinary approach with continuous monitoring of the interacting variable. And the example that I have proposed maybe fall within this part, because the example of the Visconti bridge is an example of how advanced technological scientific skill may help in the design of sustainable solution. The example of anchored wire mesh again is an example of advanced scientific skill may help in this optimization problem. The example of the railway stabilization on the interaction between pipeline and landslides is an example where the solution is dominated by the monitoring system, though in my opinion this example can be of much interest. And the last consideration is that we are not only asked to perform one sustainable step, but we are asked to perform one sustainable path steps. So that's why it's so important to take into account all these aspects. I hope to have respected the time, and I thank you for your attention.
Thank you again. And do we have some questions? Andrea? No, today we don't have questions, so we can move on to the next speakers. Thanks again. We have Professor Paolucci on new seismic hazard map.
Let us start this presentation. First of all, okay, I skipped the first slide. The nice title that you see, Internal Ramblings over Italy's New Seismic Hazard Map, is not actually by myself. It is actually borrowed by an article that was published in Nature Communication by a freelance journalist, Chiara Sabelli, about the development of the new seismic hazard map of Italy. Italy now relies on a seismic map approved in 2004. It says seismology evolves, the map must be updated with data and knowledge produced in the last decades. And for almost 3 years, the approval of an updated map has been delayed again and again, as two institutions, DPC, Department of Civil Protection, and INGV, Istituto Nazionale di Geofisica e Vulcanologia, involved in the process failed to agree on its final form. The process that Nature Italy has reconstructed through official documents and interviews with its protagonists offers a glimpse into how earthquake science is undertaken and highlights the tensions that emerge when scientific advice is translated into policy. And this is precisely related to the introductory lecture by Richard Bradley. Okay, since I am actually one of the protagonists of this story, I will give you in 15 minutes, so it is a mission almost impossible because as you have seen the story that is lasting since about almost 3 years. Okay, I will try to give you an overview of what is happening. It is a story without an end, so whenever you will consider it, you will not miss the end because there is not an end. So let us start from the starting point. This is a seismic hazard map of Italy. That is resembles the one that was shown before for Japan. It shows the values of peak ground acceleration having on rock having 10% exceedance probability in per togliere quella roba lì, non lo so. È rimasta. Ok, grazie, molto gentile. Ok, having 10% exceedance probability in 50 years, and that corresponds to a return period of about 500 years. This is the official. Okay. No, tanto pazienza. Title was the current seismic hazard map. It is the model MPS 04 because modello pericolosità sismica that was published in 2004, and it was also introduced as a law in Gazzetta Ufficiale in 2006. This is actually the basis for input for seismic design, so that its actual relevance from the practical point of view, it is that at each municipality of Italy, you have to consider this map or related maps related to other quantities other than PGA, peak ground acceleration, to define the seismic input for design. So each pixel in this map has its own relevance. It is not just a set of colors. This was actually, this is a probabilistic seismic hazard. It is based on probability theory that accounts for a number of input information with a substantial amount of certainty. So starting from a seismogenic model, this is, for example, the map of the area sources that were considered for deriving this model. Two, uncertainty related to the processing of the earthquake catalog, establish what is the completeness interval, how many centuries, 3 centuries, 4 centuries, 8 centuries, or whatever. Modeling the observed annual activity rates, how many earthquakes per year occur in each seismic area, the Gutenberg-Richter relationship. And also how the ground motion propagates from the source to the site of interest. There is the empirical ground motion models. At those times, so about 20 years ago, this was accounted for. The related uncertainties were introduced with a classic approach to account for epistemic uncertainties, that is, logic tree approach. As you can see from the picture, this was a relatively simple logic tree with a total of 16 branches, each weighted by a certain criteria. But in any case, the structure was relatively well-defined, rather easy to be explained and understood. It was the mixture of a cooperation of a product of a cooperation of seismologists and engineers. Okay, all of the scientific products may have some internal debate, and there have been in the years different subjects of debate. Why 10% in 50 years and not, say, 2% in 50 years? Why a probabilistic map and not a deterministic map? Maybe considering instead of, say, probability, the maximum credible earthquake. Now, giving the rise to the question, okay, what is the maximum credible earthquake? What is the uncertainty in such a definition, since we don't know, or we know very little about where the seismic faults are and so on. Is a probabilistic seismic hazard model a scientific product? That is, from the point of view of science, is there a possibility to falsify the model? That is there a possibility to say that, okay, these values are not correct? There is no, because the earthquakes occur with such a fortunately low rate that you will not be able, maybe in some centuries, you may be able to understand whether this was were realistic results or not. But this also gives rise to the problem of, okay, falsification. If an earthquake occurs and the PGA is larger than the mapped value, is the model false? Okay, of course this is not, because it is just 10% probability of 50 years. So it is almost certain that somewhere in Italy there will be some points that will experience a PGA larger than that. How to handle the epistemic uncertainty? The very much larger epistemic uncertainties than in 20 years ago in the previous model were considered. And eventually the MPS 19 model came. MPS model, you can call it a seismic, that was actually published in 2019, published. It was delivered by INGV to the Civil Protection Department in 2019. Now we have a situation that much more complicated, I would say, because instead of, say, for example, as in MPS 04, a single seismogenic model, the picture that I've shown before, we have 11 different seismogenic models, because whoever could propose his own model. Some are based on area sources, some based on fault sources, geodetic models, and whatever. 11 models, each subdivided in many submodels for a resulting accounting for the epistemic uncertainty with some about 1,000 branches of the logic tree. Okay, we may live with that, but in any case, you end up with something that is really a kind of black box as a final stage. These are not maps of hazard maps. These are just to give you the idea of, unfortunately, this is the title, but in any case, MPS 19, the activity rates, the annual number of earthquakes of magnitude larger than 5.5, it is not seen, larger than 5.5 according to the 11 different models. If you look at these maps, okay, they look rather similar, but actually the number of earthquakes of magnitude larger than 5.5 should not be so much variable from one model to another one, because in Italy we had many of such earthquakes in the past, say, 7, 8 centuries. So it is hard to understand, for example, why this model NA3 in eastern Sicily gives almost nothing. And I recall that in 1693 there was an earthquake that completely devastated throughout eastern Sicily, Catania, Syracuse, and so on and so on. Almost nothing, you cannot see, but Lombardia has a larger number of activity rate than eastern Sicily, for example, in this case. There was a very major variation. Okay, everything science with capitals, but in extreme variability. The weights that were given to each of these 11 models were given, I would say, in a rather different way, and also by, say, 3-4 experts, I would say. So the whole process for reaching the final result was really difficult to be interpreted, and eventually, in May 2019, as a member of the Commissione Grandi Rischi, and I also am the head of the seismic risk group of the Commissione Grandi Rischi, we were submitted this model for evaluation, for a policy evaluation, I would say. That is, we were not asked to establish whether this was we are not asked to establish the scientific value of this product, because there were other committees that did such a thing and said, okay, it's a very good high science. But we were asked to establish the applicability from the application point of view. That is this model applicable in the normative sense for seismic risk evaluations? If you look at the previous one, the new one, okay, you may recognize it is not that clear. It looks rather similar, but here the shades of red are much stronger. If you see, for example, eastern Sicily, here it is very dark red. This is almost, say, light yellow. There are other some, the Calabria, for example, all this part is relatively dark red. This is orange. It is orange in the same way as also Emilia. Okay, let us say that this was really contrary to our feeling of seismic risk in Italy, that all in all is depicted by this map. This is a map that depicts the highest value of Mercalli intensity for municipalities of Italy. That means that the darkest values are those municipalities that experience at least once, the past, say, few centuries, once a degree 10 of the Mercalli scale. Degree 10 is almost complete devastation. While the previous model was more or less mimicking such a situation, this is really something very different. For example, I realized that Bologna had the same level of hazard as Reggio Calabria. Okay, Bologna experienced in 8 centuries a single intensity 8. Reggio Calabria experienced, we know quite well, not only the 1908. But I'm about earthquake. Also by measuring the differences between the previous model and the new model. For example, we call it as the French flag. The blue ones are lower values, lower than the previous model. The red ones are the values that are higher than the previous model. So, in essence, at the end, we were very worried potential consequences of a direct application of such a model, because this would have ended up in some regions of Italy, in some areas of Italy, to completely different values for design with respect to the previous ones, with a scientific background that really was hard, at least in our opinion, to be explained, especially because it came out from such a huge machine of this immense logic tree. We asked INGV to produce something that could have been more manageable from a practical point of view. That is, to extract from these huge logic trees only those branches having the best consistency from the historical point of view. You are not actually, earthquakes are rare events. You may have an earthquake where you do not expect it, but at least when a consistency with the historical means that at least you put a threshold of stability for new models. Otherwise, really, each model, each group of scientists can produce their own model and claim that they are the best ones. So, simplify the model, having extracted those branches with the closest consistency with the historical catalog. This was really a matter of, because it took 1 year for the INGV to restart this type of work. So, so the MPS 19 was, we criticized it. Then eventually in February 2022, this new model with the single extraction was released. But it was also criticized because it was too simple to account for the epistemic uncertainties. In the meantime, a new European probabilistic seismic hazard model has been released, and of course, as you can imagine, the different models do not talk so much to one another. In the meantime, the president of INGV declared himself against whatever of such models. In the meantime, there is an impressive, a very dramatic institutional conflict between the Civil Protection Department and the INGV. In the meantime, there will be the change of government, and probably the head of the Civil Protection Department, I don't know whether it will be kept or changed. In the meantime, we are about to finish our mandate, so nobody knows what will occur next. Thank you very much.
I just wanted to know a little bit more about what these different models are. Are they models being produced by different research groups, or are they models that you get by taking the same sort of model structure but changing parameters a bit?
No, unfortunately, it is the right question. Whence these 11 models came from?
Yeah.
Actually, they came from a call by INGV to research groups throughout Italy. Either your own seismic hazard model, and then okay, so that say 5 of them, for example, are based on the same idea, area source models. So they overlap a little bit. It would be much more meaningful to have a single model based on area sources, a single model based on faults, a single model based on geodetic measurements. In this way, actually, many things were overlapped, so the level of epistemic uncertainty for the 5 models having the same source is hard to be measured. In any case, what really was the matter, it was impossible to understand whence the results came from. It was really impossible because, okay, thank you.
Okay, thank you. So we move now to the next presentation, which is going to be delivered by Lorenza, Petrini, and Luca Zanetti, and it's titled Ensemble Modeling and Credibility. I guess Lorenza, you first. Okay. Good. So floor is yours. Thanks. Ali.
Thank you very much, Stefan, and good morning to everybody. This presentation is strictly related with the Richard presented us before and what also Roberto talked about now, just now. And this is because it is this presentation stems from an interdisciplinary interaction between two philosophers that are Luca, that here with me, and Daniele, and an engineer that I am. And Luca was a postdoc here until September. Now he moved as a researcher in use, but still this work was done together. Same. Sì, giù. Su o giù?
Può darsi.
Was strongly supported by the rector, and the idea was to combine skills and teams of humanities and social science with the culture of Polytechnic. Non devo schiacciare l'uscio? No. Okay. And for this reason now there are philosophers and sociologists in several departments of Polytechnico that are grouped in a so-called meta group, and it is possible to perform very interesting interdisciplinary works about that takes into account the philosophical and ethical and epistemical aspects related with the process of science and technology and innovation. And in this context, with Luca, Daniele, we started to think about the epistemological and ethical aspect of risk and focusing on seismic risk. And we started with one of the components of the seismic risk, which is the hazard, seismic hazard. So we have already heard a lot about. We know that we are talking something that is very full of uncertainties, and so we have to use a probabilistic. We have to use what the common way to approach this problem is a probabilistic approach. Just a few words about the probabilistic seismic hazard analysis for the people not familiar with. The aim is to calculate the probability of exceedance of a specific ground motion intensity level in a given site and in a specific time interval. And this procedure needs several steps, as we have seen before. So we started with defining some models, probabilistic models, about the occurrence of earthquake in time and in space. We have also defined the so-called earthquake rate model, that is the relationship between the relative frequencies of occurrence of earthquakes and the magnitude. Again, we have to define the ground motion model that is a relationship between the attenuation of the motion with the distance as a function of magnitude and other parameters. And finally, at the end, we are able to evaluate the probability of exceedance for various levels of shaking intensity. So clear, we are introducing models and models, parameters, and that means a lot of uncertainties. And we well known that we have some so-called aleatoric uncertainties that is intrinsically related with earthquake, because we don't know exactly when an earthquake will arrive, how much it will be strong, and so on. But also the so-called, we have heard about a lot today, epistemic uncertainties. Our problem is that we have catalogs that are too short, so there is a severe lack of data, but also we are ignorant about the physical phenomena that are related with the currents of earthquakes. And that means that obviously these uncertainties strongly affect the models and the parameters that we put in these models. So as Roberto showed us, the normal approach is to take into account epistemic uncertainties is to use logic tree. And one very simple logic tree we have just seen before, somebody, we don't know exactly who, selects some models that are developed from experts, put together these models, and also there are somebody else usually that gives some weights to each models. And usually there is a panel of experts that decide that one model will have a 60% of probability and the other one 40% and so on. So in this case we have at the end 16 different models that will give us different values of the intensity, the ground motion intensity level we are looking for. And at the end there will be all the results of this model will be together and we obtain a distribution of the output we are interested in with percentile and so on. So, which is the aim of the presentation? The idea was to start to think about some challenges that are strictly related with the application of logic tree and the use of expert, panel of experts. Also, as Luca will explain, we try to give some alternative approaches to the common way to make probability systemic hazard analysis. And the problems are mainly related to epistemology, so we have some epistemic challenges. Why? Because first of all, if you want to apply logic tree, we should be sure that we are including all the models to satisfy the principle of collective exhaustivity. Also, we don't have any overlap between the models because we have to satisfy the principle of mutual exclusivity. And this, in practical, from a practical point of view, is very, very difficult, as Roberto said before, answering to the question of Richard. Second step, we are talking about something that is very, very uncertain, but we ask to the expert to give some probability in exact number. I want to know if this model will have a probability of 61, 71, whatever. And clearly we are asking something that is not feasible at the end. And finally, the problem is, what is the results of this logic tree? We have an integrated model, an aggregated model. Probably nobody will believe that the results of the model is true, is correct. Because they are just mixing the knowledge of the community. For sure, that model will represent all what the scientific community knows. The result is of nobody at the end. And this is also a problem from an ethical point of view, as we will hear later. There are some other approaches in the literature. For example, the one that was developed here at the Polytechnic is called credibility. Try to avoid the logic tree and to use statistical tests in order to prefer some model with respect to the other. There are some other approaches that still use logic tree, the confirmation approach, but they try to avoid expert in order to give some weights to the different models and to use the capability to evaluate, to score the capability of the different models in forecasting performance with respect to some observed data. I don't want to go in detail, we have no time, but in any case, all these approaches have some drawbacks that allow to be used commonly in the practical life. So now Luca will explain you another possible approach.
Thanks. So the next step of the project was to look at different ways of representing the epistemic uncertainty, especially the opinion of the expert, not using probabilities. So what to do with the experts? So the first application that we consider, and now we will go on with the project in collaboration with the department and with Meta, we have been to look at the confidence approach. Because the approach that was already introduced by Richard in his talk. So the idea would be to ask the expert to express not a quantitative judgment, so not a probability, but rather a qualitative level of confidence. For example, low, medium, or high confidence in a specific estimate. And notice that this is similar to the current practice in other fields, for example, in climate change modeling, especially the reports of the Intergovernmental Panel on Climate Change. So this may also way to reach different practices in different areas. We already see the basic formalism of this confidence approach developed by Brian Hill and developed by Richard. So you have again a set of probability measures. In this case, you have the models in your Ensemble give you basically different hazard curves. And these probability measures give you the starting set you consider. Then you have an asset family of sets, which are the sets we saw before, which represent the confidence levels. The expert, in particular, each set corresponds to a confidence level. So you have a set for low confidence, medium confidence, and high confidence. If the scientist has high confidence in a particular interval, here means that the scientists believe with that level of confidence, so with high confidence, that the true or real frequency, for example, is within that interval. And then you have, as we saw, that outer set correspond to higher level of confidence and inner set correspond to a lower level. Now, part of the work that we have done is to try to apply this approach to probabilistic seismic hazard analysis. So the idea is, again, to have the ensemble of model. The ensemble of model into the interval of value that you consider. The expert the available data and scientific evidence to provide a confidence ranking. The thing here is that you don't get the expert to judge each particular part of your model, but just the final estimate. And differently from what you find in the literature, you can also, we expect experts also to express their credibility, their confidence levels with each shape. So, for example, suppose that you have two different models that give you different, for example, PGAs for the site of interest, and maybe you have exactly the same confidence in both models, then what you end up is this kind of presentation, which the expert have equal confidence that the real value is somewhere here or and then it will be up to the decision maker to determine which level of confidence it's needed to for a decision. And so you can have a decision with high stakes or lower stakes. As we saw, this can make a difference which level of confidence, about which levels of consider. Final words on ethics and the ethics principle, which was the point we want to reach. So, especially in the last talk, there was a mention of what in another paper, Lorenza, Daniele, and I called the no-one's model problem. And the no-one's model problem is just the idea that if you get all the experts to assign weights to different parts of the model, and then just put all together, the final model that you get, the final logic tree, is in an important sense no one's model, because no one's is really a scientific responsibility for the final estimate. In this approach, by contrast, you may have actually ownership of the final results, in particular because you do not multiply the results of the model by the weight you assign using the expert, but there is a clear distinction between those who propose the model, so they are responsible for the final estimate given by that model, and the expert that propose a confidence level which is not already being built into the model. And also this approach is usually clear and more usable by decision makers that do not get a unique estimate, for example, the mean hazard or some percentage, but get this confidence levels. And I think we're done. Thank you.
Thanks for the presentation. And so we have time now for questions. Please, Roberto.
Just make a comment. Actually, I did not mention, but the weighting system for the MPS 19 was only on the models and not on the results. And this actually made a huge confusion because we were eventually the only ones who considered actually the results. The model can be, okay, a fantastic model, but okay, maybe some parameters may be wrongly calibrated and so on, and the final results may be wrong. As we know from finite element modeling or whatever, it is not the modeling itself that the fact that we are using a finite element model that guarantees that the results are okay. You should put the right parameters and so on and so on. And this is something that, for example, would have helped the decision process for the MPS 19 much more than it was at our ends.
Yeah, no, it was not a question. I got it. Okay, any other questions? Okay, so if not, let's take again speakers. So it's Luca. So we can move now to the next presentation, which is going to be delivered by Daniele Bocchiola. And the title is Hazard Assessment for Extreme Snow Avalanches, Recent Findings and Application. You can manage with your point.
Okay, I take my own.
Okay.
So I think I can manage. Okay, thank you. I think also the title changed a little bit, but never mind. Thanks to Stefano, Chiara, and Paolo for inviting me. And I must stay nigh to the microphone. Okay, so thanks a lot. I'm sharing with you today some concepts and recent findings about extreme snow avalanche assessment and zoning, etc. Well, recently there was the very famous, unfortunately, event in Rigopiano Hotel, which hit the headline, in fact, but in reality, avalanches every year in the last 30 years or so have taken, in fact, a death toll in our mountains, in Italy, in Switzerland, in France, etc. And thereby, ever since 15 years or so, we thought that it was worth maybe studying and investigating the stock for hazard mapping, etc. Either way, we did a lot of work together with the most famous scientists in the field, which is the people in the SLF Davos, which is the Federal Center for Snow and Avalanche Investigation, to whom we owe a lot of knowledge and a lot of cooperation. Either way, I'll show you a little bit of recent investigation also related to the topic of climate change impact on potentially modified for snow avalanches, because of course the common thought is that the snow is not going to be here with us anymore very much in the future, but in reality it turns out that some extreme event may still happen, in fact. Well, here we have a menu, and I will introduce some details about avalanche mechanics, etc., and then also some case study and results. In the last few years, we had a number of interesting projects related to the topic of avalanche. One, for instance, was very recently with Regione Lombardia Authority for Civil Protection, which has asked us to provide some scientific advisory in the field of specifically hazard mapping, and especially related to climatic input, because as you might imagine and figure, the most important input to avalanche activity is, of course, the climate and snow precipitation. So, just a few numbers. Here you have a few charts, unfortunately in Italian, but basically there are indication of number of people involved in avalanche in the last 30 years or so. And in fact, also a number more or less of 20 people or so dying in Italy since 1986, which is in the last 30 years or so. So In fact, the number of people actually being involved in accident, either dying or only being involved and maybe possibly rescued and saved, it's quite high. So risk of avalanche in the mountain, especially risk upon people and human life, is in fact not negligible at all. It might be of interest to look at the casualties, and especially divided by activity. Ski off-piste, 27%, and ski alpinismo, which is uphill off-piste skiing, 8%. So you know more or less what type of activity you shouldn't be doing in the wake of a heavy snowfall. Generally speaking, 3-4 days after the snowfall, it's a very bad period. So in these few days after a large snowfall, do not attempt such activity. This is an amicable suggestion, in fact. About avalanche, well, avalanche are a very complex type of phenomena. Claudio di Prisco illustrated something about landslides. Well, many things, many concepts also apply to avalanche, because avalanche are, say, very complicated type of phenomena, because they involve basically a material which is a mixture of ice, water, air. So it's quite a complicated type of mixture, and there might be very different type of avalanches. There might be very small slough, as they call them, which are point-wise avalanche that then spread triangularly, and normally very little volume is involved. Or powder avalanche, like the one here. Powder avalanche normally starts with a very fresh and very dry snow, very light, that moves down a slope, and then maybe they hit a rock or they hit an obstacle, or there is a sudden change of slope, and basically the mass blows up. And you have this very powdery situation. Here, the pressure of impact of the avalanche, which is an important parameter, is very low. Notwithstanding, these types of avalanche are very, very dangerous. If you are in the neighborhood or in the vicinity of such an avalanche, you must absolutely cover your airways, okay? Because if you breathe the powder, it might be very dangerous. People literally die only for breathing this type of snow. So it's very dangerous also. Those are called slab avalanche, which is with a very large detachment front and normally a very large amount of snow, in the order of, say, 100 to 200,000 cubic meters of snow, okay? Snow weighs 1/3 of water, more or less, so it also has a very high impact pressure, okay? 300 kilograms per cubic meter to 500 kilograms per cubic meter. Okay, so the impact pressure may be very high. But the velocity, in fact, can be tenfold as the velocity of water normally during a flood. So 2 meters per second for water, 50 or 60 meters per second for an avalanche, which is 200 or more kilometers per hour. With that weight, of course, it's very dangerous. Again, this is a small dry surface avalanche. So it's a very complicated phenomenon. In terms of stability, it's very interesting that basically the theory for soil stability can be applied. So a more long type of approach, where in fact it is even possible to measure cohesion and friction of snow as a material with this type of test, triaxial test, etc. However, they are not used very much in practice, because the variability of the material is so high that it's very difficult to in fact establish such parameter, and it can only be done when you do on-site in situ tests for determining such type of parameters. So in practice, normally for the purpose of civil protection, it is not very much of interest, let's say, the detaching mechanism. It is more important, of course, what happens after, which is the dynamic part or the dynamic phase of the avalanche. Difference from avalanche, of course, as in civil protection method, there are different type of activity related to control of avalanche themselves or control of their position. Scientifically speaking, at least from our point of view, probably, let's say that the most interesting part are related to permanent structure for avalanche control, such as active and passive structure, which is snow rakes, snow walls, etc. And on the other end, of course, the land use planning and design, which is hazard zoning and then subsequent constraint on land use, of course. Why am I saying so? Because in both these activities, it is important to know, well, on the one hand, the dynamic of avalanche, which is the way avalanche dynamically behave. And on the other hand, a little bit more of our know-how, for instance, here in Polytechnico Historical, which is about the statistics of snowfall and extreme snowfall. So it was in these two type of topics that we engaged a little bit ourselves in the last few years. Here you have some examples, snow bridges, snow nets, snow rakes, etc. All of these basically require an assessment of the snow depth to be dealt with, which is of course related to later period of snowfall, etc. So statistical concept, which again historically are being developed a lot in our school here in Polytechnico. And also, check dams. For instance, this is a snow wedge. You see, it's a very high structure. The purpose of such a structure is basically to confront the avalanche running and basically blow it up in a snowy situation. Because doing that, you basically decrease the density and you decrease the impact. Of course, the power, going everywhere can also be a problem. But in this case, it's important basically to dissipate the incoming mass. A little bit about the theory of avalanche dynamics. Well, we have basically mass conservation equation with these two terms, which are erosion and deposition, basically, which are very difficult to model quantitatively, not modelistically, but by measurements, because of course you can imagine that nobody can, stay very close to an avalanche when it happens and do measurements. The second end, we have basically momentum conservation equation, and this is basically shallow water equation, the Sunderland equation, with some modification, however. And probably the most interesting part is the constitutive law of the snow, basically of the mean, which is a static dynamic mixture, or as they say, Newtonian with a threshold. The threshold being given by this term here, which is basically a static friction, and this mu parameter is basically an angle of friction or a slope of friction, which is necessary in order within the model to stop an avalanche when it's moving. Because basically at very low velocity, no friction would be developed according to the classical Newtonian theory. So you need to add something which basically dampen the velocity of the avalanche and make it stop. So this is a very important and key parameter. In terms of exposition, well, rather in terms of hazard, with the classical Vance equation for risk, what we are more interested in is basically the evaluation of hazard, which is the probability or return period of a certain event. In this case, and here we inherited something from our Swiss colleagues, and especially this Swiss procedure, as it's called, and this is used by INEVA, the Italian Association for Snow and Avalanche, and now it's also applied as a law, as a rule, because in 2019 there was an Italian regulation which basically gives indication for snow avalanche hazard mapping all over in Italy by application of this procedure here. The Swiss procedure is a bit changed in Italy. It's basically the same conceptually. We work with return periods, which is we define basically 3 return period of interest, which is 300 years, 30 years, and also in some cases 100 years. And then we work with pressure of impact. So when the pressure of impact is above a certain threshold and the return period is even high, you are in a red zone, very dangerous. But even if the return period is low and still you have a certain impact pressure, because the return period is low, so the probability is high, you still are in a very high danger areas. And the blue zone and yellow zone are normally less dangerous area. A very important thing in order to apply this model is, first of all, the assessment of the return period. Return period of what? Because no avalanches are basically driven by snowfall, we work with what we can call a derived approach, as we do, for instance, in hydrology, which is we attach to the avalanche the return period of the generating meteorological factor, which is the snow depth. And particularly, we consider what we call H72 or H3D, which is the amount of snow fallen in 3 days. Because in Switzerland, according to many tests that they made in correlation analysis, this is the period that is necessary for snow to settle. After these 3 days, you should be more or less safe that this snow layer is not going to fall very soon, and it's probably going to settle, and then either melt or possibly be discharged and disengaged, but later on in the season, maybe with lower depth, etc. So we concentrated a lot on the estimation of this H72. Here, well, it's not very visible, but there are a number of dots here which are colored in dark blue and white. And these are all measuring stations of snowfall depth managed by, ARPA Lombardia, basically, in conjunction with the INEVA association. And using data from this network of stations, we were able to basically set up a method, which is a regional method, usable to assess H72 with a certain rater period. The map you see here is the mean value, mu H72, distributed with a Kriging procedure all over Lombardia region. And basically, the civil protection of Lombardia authority is going to use this map as a base map, as a benchmark map for professionals, for anybody basically providing a snowfall assessment for the purpose of hazard mapping. Of course, as a benchmark, because locally different methods with different results may be applied. And on the other hand, and this is called the index value. This is, in fact, called an index value approach, which is we have the local mean, and then we have another term, which is the A72 star, which is called also growth factor or non-dimensional factor, which provides the variability in terms of extreme values, which is with high rater period, spread all over the region as if the region was homogeneous, which is in all the region, this distribution of the extreme value would apply. Professor De Michele knows better, in fact, because he's been working a lot on this topic in the field of hydrology. And this function, which is the dimensionless value of H72 all over the region, is plotted here with the dots, and there are very many dots because, in fact, the regional method profit from taking few data from many stations, which pulled together become a high number of data. A good and viable estimation. Here, particularly, we use the general extreme value distribution, which on the Gumbel chart, in reality, is almost aligned. So basically, we're using a Gumbel distribution. Okay. So I have to run. Well, this method can be applied. Here we have an example on a valley, on a mountain site of northern Italy, the Vallecetta mountain. Also Professor De Michele knows a lot because it's in Bormio town. In 1983, we had the largest event, which is two subsequent events on May 1 and May 16. And the blue one mapped here is the second one, which glided over the first. So provided, I think a few people died here and there was a lot of damage. And by applying this regional procedure plus the one-dimensional modeling, we were able to establish basically the red zone and the blue zone as they are sketched here on the ground map, on the ground layer map. And here we represent what we call the variability of the estimate. Talking about uncertainty, we basically were able to use the regional method, for instance, for the red zone, to basically define a red zone, an average, I would say red zone, plus minus something, and you only see the minus here in reality, which is this span here is the range of uncertainty which we have of the map. While the local method, that is using only data from a local snow station, would provide this type of uncertainty. And the same with the blue zone, okay, regional and local. So using this method, we were able basically to confine a lot, to constrain a lot the possible uncertainty in mapping. And this is very important because, by the way, beyond this red line, which is the red zone, beyond on the right part, probably some constraint on building and land use planning, etc., would be applied. So the bigger is the uncertainty, the bigger is probably the belt where you would apply, some cost. Very quickly about the climate change, we did some simulation. That is, we used another model developed by Giovanni Ravazzani during his PhD. And we did some simulation with many different models at the mid-century and at the end of the century, and let alone the different models, etc. But what you can see is that the red, blue, and yellow zone in reality can change a lot, and you can see all these lines with dots, etc., indicating that in some cases, for instance, here at mid-century, you can have a red zone which is much further than the present one, indicating that notwithstanding a very, higher temperature than now, and possibly lower snowfall on average, some extreme event of precipitation, which is with high snowfall, may still happen during the coldest periods, providing then the snowfall, avalanche events, which would go farther and will provide further damage downstream. Okay, so apparently we need to reconsider a little bit this hazard mapping in the face of what's going on with climate change. A very last slide about gliding, which is a very interesting phenomenon, which is the viscous movement of snow until it detaches. And it was very interesting that a few years ago, we were able to use some measurements of deformation in time of the snow, which is this black line here, together with our colleagues from University of Turin. And we were able to make a preliminary model which in fact can describe, as you can see here, quite well the rate of deformation of the snow layer until breaking. This would be very interesting because if you can drive the model with forecast of local snowfall and temperature, in principle, you would be able to forecast the snow deformation until rupture. And so give a sense of the increasing risk for avalanche detachment during one period. Okay, so a few conclusions. Again, watch your track when you go skiing and walking and climbing in the mountain, because as we said, it may be very dangerous, in fact. Okay? Thank you so much.
Thanks, Daniele, for the presentation. So we have time, as usual, for one question. Yes.
Thank you for the presentation. Just a curiosity, because going to the mountain, we are noticing that the morphology is changing because of the weather, because of the hot, so there are no more, the ice is no more there. So you find that there is a very cracked rock. And so my question is how these changes of the morphology of the mountain could affect the models in terms of avalanche, because the snow is no more, and do not find the same land, let me say, when it arrives.
Yeah, thanks for the question. Well, on the one hand, snow is a seasonal process. So never mind what happens with glacier, with landscape in a sense or whatever, but what is important is the seasonal cycle of snow. And also it's very erratic, like precipitation. So in some cases, you can have a very dry periods, very long dry periods with no snow, and then a sudden precipitation event. And if it's below the thermal zero, you have a flood. If it's above the thermal zero, you basically have a snowfall and snow deposition. And on high slopes, then you can have large avalanches. So in a sense, this is disconnected for the general climate situation. It's really related to single wet spells that can still happen very intensely. With relationship, for instance, with the ice topic, such models, these dynamic models, can also be used to simulate the spreading, for instance, of ice avalanches. So maybe they can be used to model the crevasses, the breaking of crevasses, like the one of the Marmolada mountain this summer. And in principle, if you were able to forecast the detachment of such a chunk or piece of ice, you could have modeled the downslope spreading, and you could have made a map of hazard, for instance. I think that these methods should be applied now nearby glacial cover area, because in this historical period, this type of hazards are going to be more and more frequent. And I think that these maps should be done, and possibly passage of people during summer within the hazard zone should be limited whenever possible. In my opinion, of course.
Okay, thanks.
Thank you.
Thanks, Ivan, for the discussion.
Thanks, Daniele. And now we can move to the next presentation, which is going to be delivered by Giovanni Ravazzani. Whose title is Propagation of Precipitation Measurement Biases into Hydrological Simulation, a case study.
I will show you some results about a project, a PRIM project, reconciling precipitation with the role of understated measurement biases in the modeling of hydrological processes. So in this project, we investigated two sources of uncertainty in precipitation measurements. The first source of uncertainty is due to the mechanics of the equipment that is used for measuring precipitation. The usual gauge is based on a tilting bucket. So actually the measure of precipitation is a measure of the number of tilts in a given time interval. And this can cause some mechanical errors. And the second source of uncertainty is due to the environment, in particular the wind. So wind impacts the instrument, the rain gauge, and this can modify the velocity field around and above the equipment, and this can change the distribution of rainfall, so the amount of precipitation of water that is measured by the instrument. The case study is the Seveso River, so the river in Milan. So in this basin, that is an area of about 200 square kilometers, so it's quite a small middle basin. We investigated 5 rain gauges inside or just outside the river basin. And so this is the field campaign, some photos from the field campaigns to derive to assess the uncertainty due to the mechanics of the instruments. So we use an equipment that is actually a tank that can produce a constant flow rate. So you can change the flow rate, and so we put this equipment above the rain gauges, and so we could assess the error of the instrument. This is the family of errors. So we can recognize two types of okay. So, this line, the upper line, that has a zero error for 50 millimeter per hour intensity, and other ones that have a zero error for zero precipitation. This is because this type of equipment can be calibrated in order to have to reduce the error for a given precipitation intensity. So these equipments were provided by different companies, so that's why we have different error curves. For the assessment, sorry, just to note that so generally for the most of the rain gauges included in the analysis in the investigated area, we have an underestimation of precipitation intensity that can reach the more than 10% for high intensity rainfall. And for the second source of uncertainty, so the wind-induced error, we performed some experiments in the wind tunnel facilities of Politecnico di Milano in Bovisa. And so the idea was not to simulate rainfall event, but just to put some water drops inside the wind tunnel, and to measure detect the change of the pattern of the raindrop due to the presence of the rain gauge. So we used a camera to detect this pattern, and these are some results. So this is a work that was performed by the colleagues of the University of Genova. And so on the left, we see the disturbed pattern of the raindrop, and on the right we see the simulation results. So a fluid dynamic computational model was used to so it was calibrated, and so it could reproduce quite well the pattern of the raindrops. So using this model, so a fluid dynamic model, some precipitation events were reproduced by the model. So this was used to assess an equation to define the collection efficiency of the instrument. So this is for a given type of instruments. We see that there is a relationship between the collection efficiency, so the rate of the real precipitation to the corrected precipitation. And this equation is a function of the precipitation intensity and of the wind speed. And so we see that for low wind speed and low precipitation intensity, the collection efficiency is greater than 1. This means that the rain gauge is affected by overestimation of precipitation. For high intensity rainfall, that means larger drops and high value of wind speed, we have an underestimation of the measurement. And so we use this information from mechanical error and wind errors to assess the impact on the hydrological simulation. So we considered 5 events, and now I show you the results for the 2 events in July and October 2018. So just the first analysis is about the precipitation. So this is the measurement. So for the July event for the Como Villageno rain gauge, and on the upper left we have the precipitation intensity and the wind speed. And we see that for the combination of precipitation intensity and wind speed, we have a collection efficiency that is greater than 1. So we have an underestimation of precipitation. On the lower right panel, we see the gray is the gross rainfall, so not correct precipitation, the total amount during the event. The blue one is the one corrected with the the error for the mechanical issues, and the orange one is for the correction, so the accumulation of mechanical issues and the correction for wind speed. And so we see that there is an underestimation that was corrected, so by the 3.5% and 4.4%. For the second event, this is the precipitation measured at the Cinisello Balsamo rain gauge. In this case, this was an event that occurred in October 2018, and the precipitation was very low, so the precipitation intensity was low, and even the wind speed was low. This led to a collection efficiency greater than 1. So this means that the rain gauges was affected by an overestimation of the precipitation. And this is the effect of the correction on the gross rainfall. So the mechanical error that detected an underestimation was corrected. So we increased the precipitation by 3.4%. When you put the correction for the wind speed, was an overestimation. This compensates partially the underestimation due to the mechanical issues. So transforming this information, so precipitation into the runoff using a spatially distributed hydrological model, so we put 3 different inputs in the model. So the first is the precipitation not corrected, so the gross rainfalls. The second is the precipitation corrected for the instrumental bias, and the third is the precipitation corrected for instrumental bias and wind-induced errors. So this is the results for the first event, the one that occurred on July. So this is the simulated discharge and the observed discharge, and we see that the impact on the peak of the flood for the mechanics correction is nearly 9%. With the error for wind speed, the difference was 10%. In the second event, so we have so with a similar approach. Sorry. So the difference in the peak discharge was 4.5% for the mechanics correction, and for the wind correction was minus 1.45. So the low intensity, the low wind speed that introduced an overestimation compensated the error induced by the mechanics of the instrument. And so these are the general overview of the results for the 5 events considered. And so there are some, in some situations, so when the rainfall intensity is low and the wind speed is low, we have a reduction of the peak discharge. When the intensity combined, when the high intensity rainfall combines with the high wind speed, we have a combination of errors, so the difference is larger. So conclusion, the instrumental bias, at least in the station that were investigated, can reach more than 10% for high precipitation intensity. The wind-induced error is relevant when the high values of wind are measured, when wind speed is low, wind-induced error can compensate the bias due to instrumental issues. In these specific, the specific events and the specific area that we investigated, so the maximum total precipitation bias was 0.4% with an impact on the discharge of more than 10%. Thank you very much.
Thanks, Giovanni, for the presentation. My usual questions. Do you have questions?
I have one, maybe.
Yeah.
Thank you, Giovanni, for the presentation. I didn't catch it at the end. You said that by tuning the model, you can basically compensate for the error in rainfall estimation.
Yeah, when you have a combination of low precipitation intensity and low wind speed, so that you have a small error due to the underestimation for the mechanical issues, and the overestimation induced by the low wind speed compensate the error of mechanical issues. So there is a positive error and a negative error that combines. And so you can, in these particular situations, the error can become zero. Generally, so when in different areas, you can have different results, of course. If you have strong precipitation and strong wind, this can lead to a great impact on the simulation of discharge.
And you think that you could do some hydrology backwards, such as you measure the discharge and you track back the rainfall, so maybe you can correct the rain gauge measurements, or there is too much noise?
Starting from the discharge, yeah, I think it's quite hard because in this particular case, so in a small basin, we found 3 different types of precipitation of rain gauges, so with different errors. So it's and every instrument has its specific error curve. So it's different to starting from the measurement of discharge in one section to go back to the single devices. And again, moreover, the discharge measurement is affected by error. So that can be in the order of magnitude of the precipitation error. So it's something that difficult to.
So you don't like hydrology backward?
Not for this purpose.
Thank you.
Okay, thanks. Thanks again, Giovanni. And so last but not least, I would say, so we move to the last presentation by Daniela Molinari, whose title is MOVIDA, How to Combine Technical, Social and Economic Aspects in Flood Damage Assessment and Mapping.
Thank you very much. So don't worry, I will try to drive you quickly to the lunch. So the objective of my talk is to present you some of the results of a project that is called MOVIDA. That is the acronym of Modello per la valutazione integrata del danno alluvionale, that is an integrated model for flood damage estimation. And MOVIDA is placed in the revision process of flood hazard and risk maps, which is required every 6 years by the European Floods Directive at the river district level. To support such a process, the Po River District Authority signed in May 2020 an agreement with 20 Italian universities and the National Research Council with the objective of transferring state-of-art about hydrology, hydraulics and flood damage modeling into the production of the new maps to be delivered by December 2021.
MOVIDA in particular focus on developing tools and methods for flood damage estimation, and was carried out by a smaller consortium of nine partners among those included in the original agreement. Well, this slide synthesize how flood damage and risk was assessed before the development of MOVIDA. So I will try to use the pointer. No? Non lo so. So the first step was the identification of a potential damage for each kind of exposed assets according to an expert-based evaluation. Then this information was combined with the hazard level coming from hydraulic modeling into, again, an expert-based risk matrix to obtain a qualitative evaluation of risk in classes ranging from low to high. Now, it is evident that such a result cannot support any kind of cost-benefit analysis or even better multi-criteria analysis of the mitigation actions that must be included in flood risk management plans. And this was just a big limitation that was also highlighted by the European Commission in its evaluation of the Italian plans. So the main challenges faced by MOVIDA were related to identify the quantitative, physically based damage models that are calibrated and validated for the Italian context, whose results can support the identification of the best mitigation actions. To do that for all the categories of exposed items identified by the flood directive, to use as input of such models institutional data that are available for the whole district to guarantee the consistency of the result at the district level, and finally to develop an OpenGIS information system to elaborate the input data and to represent the output of the analysis. The focus of the project was on the direct damage to the 5 macro categories of exposed elements identified by the floods directive, for which specific damage assessment tool were identified in the literature or newly developed. This slide shows how some of these categories were further classified in order to reach a more detailed damage estimation. So, for example, economic activity were further classified in residential buildings, commercial and industrial buildings, or better activities, and agricultural activities, while infrastructure were further classified in roads and railways and strategic buildings. This slide shows the main result of the project, that is a modular procedure for the estimation of flood damage assessment in the district. I cannot go into the detail of the different damage models, but the idea of this graph, is to summarize which are the main features of the procedure. What we can see is that according to the state of art on flood damage modeling, that highlights how damage models are not evenly developed for the different assets at risk, we reach a different level of analysis for the different categories of exposed elements. So in some cases, we were able to get an estimation of the real expected damage. In other cases, most of the time, we were only able to estimate the maximum potential damage, so the exposure, the value of the exposure. Damage can be estimated in quantitative terms or in qualitative terms, so in classes of damage ranging from low to high. And a final aspect regards the possibility of estimating damage in monetary terms that was possible only for tangible assets. So at the end, we have some damage indicators that are characterized by different meaning and different metrics. Then we implemented the procedure to estimate damage to those areas that are identified as areas at significant flood risk in the district for 3 different return periods. The result of such an analysis can be found in the annexes that we have prepared for each area in the flood risk management plans of the district, of the River District Authority. Here we have reported an example of such results. So we can see that we have different damage maps for the different exposed assets. Now, it is evident that the results supplied by MOVIDA represents an improvement with respect to the present state of art, both in terms of asset considered and in terms of results supply, because they allow the identification and localization of typological and spatial hotspots, but they especially they support the cost-benefit analysis and the multi-criteria analysis of mitigation measures to be implemented in the district. And these, of course, allow to compare different scenarios of intervention. But how this can be done? Well, implementing a multi-criteria analysis in this specific case means combining those indicators that are characterized by different meaning and different metrics into a unique damage indicator on the basis of which mitigation actions are selected and chosen. And in particular, we can see that the different damage indicators that we have seen before, supplied by the MOVIDA procedure, can be synthesized in 4 damage indicators. The monetary damage to residential buildings and economic activities, the number of exposed people, the number of cultural heritage sites that can be damaged in case of flood, and the kilometer of transportation network that can be damaged in case of flood. Now, it is evident that these indicators cannot be simply summed. They must be combined and weighted somehow. Well, the weight of each indicator in defining the final damage figures depends on the subjective perspective of who is doing the analysis. So, to support the definition of mitigation actions that are public choices, collective choices, our synthesis need to take into account of the perspective of a variety of stakeholders. So citizens, economic activities, public agency, public stakeholders, environmental agency, and so on. In order to do that, we implemented, with the support of Poliedra, a multi-criteria rating model that is called Electre. This model allows just to consider and synthesize conflicting perspective by consultation with stakeholders. And this allows also to compare qualitative and quantitative data with different metrics and different meaning. On the other hand, particular care must be taken in presenting the tool to stakeholder, because the mathematical process behind it could be difficult for them to be understood. And at the same time, particular care must be taken in presenting the right question to the stakeholder in order to catch their perspective. The next few slides show you the process that we followed for the definition of the weights of the different indicators. I'm not going into detail of the mathematical model because there is no time, and also because this is not my expertise. But basically, after the identification of 5 pilot areas, the first step consisted in classify each damage indicator in 4 classes, ranging from low to very high damage. And the range of each class was defined by calculating the quartiles of the values assumed by the indicator in the 5 pilot areas. Then some experts in flood damage assessment and management were interviewed as a stakeholder. In total, now we interview 25 stakeholders, but the idea, of course, is to widen such process in order to catch more perspectives. And the objective of the interview was to catch the relative importance that each interview gives to the different indicators in order to, let's say, the final sort of ranking of the indicators. Here I have reported one example of the question that we supply to stakeholders, asking them, for example, to choose one indicator to change from the worst value to the best value in case of an implementation of a mitigation action. And then the second prefer one, the third prefer one, and so on. Then, by combining the different answers from the different stakeholders, we were able to define let's say, collective weighting of the indicators, on the basis of which it was possible to calculate a total damage and to classify a total damage. Because the specific tools that we have used do not allow to highlight conflicting views, at the end we carried out a sensitivity analysis of the result by randomly changing the weights in a range equal to plus minus 10% of the original values for 300 times. And what we got was a good stability of result, with 84% of the flooded area that do not change the damage class, and 100% of the flooded area that do not change the damage class in at least 80% of the simulation. So this is the final product of the multi-criteria analysis. So now we have only one map for each area in which damage is classified according to the total damage figure. And this is just the information that is used to evaluate the effectiveness of the benefit of mitigation actions by comparing the reduction in the damage class with the cost of the intervention. So what our experience, let's say, corroborates more than highlights is that flood damage and more in general risk assessment is not solely a technical problem, but we have economic and social aspects that play a critical role. And so we need a multidisciplinary and a participative approach to deal with the problem, in which local stakeholders must be involved to define a final synthesis of the damage evaluation, because the total damage figure must reflect the values that the different stakeholders give to the damage, and in particular those stakeholders that use this information in decision making. Before concluding, I'm very proud to say that MOVIDA won the Minimax competition, launched in September by the launched in last spring by the Global Water Partnership, and was awarded as one of the best solutions for managing water and climate extreme at the global level. So we are very proud of that. And that is all. I thank you, all of you, for your attention, and of course the many researchers that were involved in the project. Thank you very much.
Grazie Daniela, thanks. Do we have a very last question for Daniela? Yes, please.
Well, I'm interested in how you pick your stakeholders. Maybe too long a question, so.
No, it is not so. Well, the idea, now we are signing an agreement for MOVIDA 2, so we are moving to the next step. This was a preliminary analysis, and the stakeholders were basically chosen according to who participated somehow in the process. So local authorities that were involved in MOVIDA, some researchers that were involved in MOVIDA, some technicians, but the idea, of course, is that if we want to have more robust results, we have to engage citizens, economic actors, and they will be the objective of the next step. So the idea was to set the method and then to widen the application in a second step.
Thanks again to all the speakers. I think that's all. And Paola will close these meetings. Thanks. So just very few words. I apologize for the delay, for sure. Just to thanks again our guests. So thank you, Richard, and thank you, Joseph. And for sure, thank you very much to all our speakers for giving us a so wide overview of the department expertise of on these kind of topics. I mean, natural and anthropic risks. I think it's a very good overview, and we are going to share all your presentations, all the videos of your presentation on our website. We'll send you an email with the link to the videos. And I like to think that it's a good starting point for our new adventure on the PNRR, which is about exactly the natural, environmental, and anthropic risks. So this is the starting point. Maybe next time we will meet to share the first outcome of the project. I hope so. So thank you, and I hope I can see you as soon as possible.